Right. I did? Okay. So your test is back. I'll go over it again on Wednesday during the problem session that seemed to be best for everyone. Problem session Wednesday, Astro Lab. And retake, it's in the testing center at the TLC. So any time between now and November 1st. So that way you can get your feedback. So before Monday is the last day to drop. Not that I want to lose anyone, but you know, it's important information. So moving on, got a rest semester going forward. And if you ever take a speech class, they tell you never to say that you hate a topic, and never to apologize to the audience either. And here I'm going to say, I'm sorry guys, but I kind of hate thermodynamics. I think this stuff is kind of boring. Actually, I don't particularly care for stoichiometry either. If you're ever wondering, like, why would this guy study years of his life to chemistry, and I mean, the reason why I did it is because it explains why the world behaves the way it does. And I just don't like thermo. I think it's kind of boring. I like the quantum stuff. We're going to do the quantum stuff next. That's fun. Quantum and why things bond and how they bond. That's fun. And the applications, too. That's cool. But thermo, one thing about thermodynamics is it makes a lot of sense. Students tend to like it because it's very straightforward. So, and moving on, we'll talk about about thermodynamics and energy. So the chemistry definition of energy is the capacity to do work. The physics definition is the integral of force dot ds. So it's the force over a path length integrated. So it's your force. So if you're moving like this, if you have a crazy path moving around, it's the work is the force moving at each integral piece. That's a better definition, truthfully, but with this chemistry class, we'll stick with the capacity to do work. And we have a couple types. Kinetic and potential are easy types. So there's other types, of course. Radiation is a type of energy, but kinetic and potential. And the old physics trick is this textbook has potential energy, and then when you drop it, I'll try not to make too much of it now. So you drop it. Now it's turned to kinetic energy. Well, now it's at rest, but the potential energy turns to kinetic energy. And you can store energy chemically, right? And that's what we do when we eat food. When we eat food, we turn that potential energy into kinetic energy. So you eat a donut and you run a couple miles, right? So you've converted that energy that way. And a couple things, though. This will always be given to you, and you remember last class we talked about this. A joule is a kilogram meter squared per second squared. And then we have the law of conservation of energy. Energy is neither created nor destroyed in a physical process or chemical process. So energy is not created or destroyed. There's a few things that break the law of conservation of energy. Nuclear reactions break the conservation of energy because matter and energy are interchangeable. Also, dark energy seems to break the conservation of energy. So dark energy, that's the reason why the universe is said to have been expanding faster. Oh, no, kinetic energy, this is another physics thing. It's 1/2 mv squared. M is mass, v is velocity. Okay, so zooming in, this is half of the battle, is picking your system. So with thermodynamics, the hard part is picking your system, and then once you figure out what your system is, doing the math. But actually, this is a hard part. What is your system? It depends on what your application is. Frequently for this will be a chemical reaction or something physical, something you can touch. And energy flow into the system is positive. Energy flow out of the system is negative. So meaning if I go into a steam room, so if I'm the system, and then I go into a steam room, and as the steam is condensing on me, I get hot. If I'm the system, that is a positive energy flow. I'm feeling hot from that steam. And if I go, then I jump into some ice water. So jump into some ice water, and I get cold. That means that heat is leaving my system. That's negative heat flow. So it's not like it's negative energy. It's just the direction. We pick the direction out of the system being negative and into the system being positive. And the first law, and this is the abbreviated first law. First law of thermodynamics is actually just the conservation of energy. And it's the change in internal energy of the system equals the work plus the heat. So if you take other classes, and the first law of thermo can have other terms. So it can be gravitational potential energy, for instance. So, but for this class, we're abbreviating it to just the first law, the change of internal energy. E is internal energy. Change of energy of the system is equal to the work plus the heat. So another thing, so no one's taken advanced calculus here, have you? No one. I don't know if anyone has. If you take advanced calculus, what about partial differentiation? Have you done that yet? Haven't done that. Okay. So if you have a function and you take the partial derivative with respect to x and y, and if this equals the opposite variable, in switching the terms, if you do this, this is known as an exact differential, which also makes it called a state function. And a state function is path independent. So E is a state function. H, which we'll talk about later, is entropy is, as well as Gibbs free energy. There's other terms that are we won't talk about this class, but Helmholtz free energy A is also. These are state functions. So work and heat, these are not state functions. So what I mean by path independent. So I can take a gallon of gasoline. I take a gallon of gasoline and I can throw it into like a wicking medium, and I can light it on fire. And I can get 100 million joules of energy from that gas. I don't know how much I get, but I'm making it up. So I can get, from a gallon of gasoline, I can get 100 million joules of heat. And so I can sit there and feel the heat, that 100 million joules burning from a gallon of gasoline. Or I can take that gallon of gasoline and I can throw it in my car. And a regular gasoline engine gets about 20% efficiency. So meaning I can throw it in my car, and then I can get, so 20% efficiency. That means I can get 20 million joules of work from that gallon of gasoline, plus 80 million joules of heat. Or I can take that gallon of gasoline and throw it into a hybrid car. That's slightly higher efficiency, probably around 30%. So that means in my hybrid car, I can get, I don't have a hybrid car, that'd be nice, but I can get 30 million joules of work plus 70 million joules of heat. Or I can throw it into a fuel cell car and get 65 million joules of work and 35 million joules of heat, right? But notice that the sum of the energies of the work plus the heat always equals the change of internal energy of the stuff that I'm using. So that's what we mean by path independent. So it's path independent. And but the work and the heat are path dependent. It matters how I use it. So whether I use it just to burn something, if I use it in a car, or what kind of car I use it in, it changes. So let's see if you can follow this. If the change of internal energy is 50 joules and the work equals 20 joules, what's the heat flow? What's the heat transfer? Some think it's 50 joules. Some think it's 30 joules. So people aren't playing. Oh, come on. Half the class is playing. It's supposed to be an easy one, right? So if this is 50 equals 20 plus x, what's x? Right, x is 30. So we're going to start with heat flow. Heat flow, and one of the ways, heat can flow different ways. Heat can flow from chemical reactions and whatnot, but I'm going to start with just simple heat flow going, and heat flow also It only happens from hot to cold. So, so when it comes to flow, things that flow, heat flows from high temperature to low temperature. So when you put your ice cream in the oven and you turn on the oven, it doesn't make your ice cream colder, right? It makes your ice cream, the heat flows from the hot oven to the cold ice cream. It doesn't flow from the cold ice cream to the hot oven and make the oven hotter, right? So that's an example of the second law of thermodynamics, which is entropy is always increasing. So entropy is disorder. So we always go from high temperature to low temperature. Also, high pressure to low pressure, high concentration to low concentration. So that's how things flow. Flow always works that way. So it doesn't work the other way. And the heat is equal to the heat capacity times a change in temperature. And C is the heat capacity, and then here, this is mass times specific heat capacity times change in temperature. So your heat capacity can also, if you have a substance, you can multiply the mass times the specific heat capacity. So heat capacity, an example of something that has a high heat capacity is water. Water has a pretty high heat capacity, meaning if you put your hand in cold water, let's say you have ice water and you want to, and you have a burn on your hand, like, oh, I need to cool this off real quick. If you put your hand in cold water, your hand gets cold, and the water is still cold, right? The water doesn't warm up very fast. You have to apply a lot of heat to water to heat it up. And also, if you put your hand in boiling water, it's going to keep on hurting. It's going to hurt and hurt and hurt and hurt. It'll burn you pretty severely. What happens with a metal, though? Metals have low heat capacity. So what happens if I put a spoon in the freezer? If I put a spoon in the freezer, it gets to be 0 Fahrenheit, so negative 15-ish Celsius. What happens if I have a spoon at negative 15 Celsius, and I say, oh, I've got a burn right there, and I put it on the burn, and it feels cold, and oh, it's not cold anymore, right? Because the little bit of heat from my hand went to the metal, and it raised the temperature really high. The opposite is also true with metal. So if I have a metal spoon in boiling soup, and then I put the soup on my finger, and like, oh, that hurts, and oh, it's not that bad, right? Because the heat will flow from the hot spoon to my hand, but then the temperature of the spoon drops really quickly. So that's what a low heat capacity means. So it depends. The heat capacity says how much energy it takes to have a corresponding change in temperature. Low heat capacity means change of temperatures happen very quickly. High heat capacity means change in temperatures happen very slowly. So metals, very low heat capacity. Water has a very high heat capacity. And are there things with higher heat capacity than water? Yes, there is. Antifreeze, so ethylene glycol. Ethylene glycol has a higher heat capacity. And like, quite frankly, if you ever wondered, why do we use antifreeze here in cars in Hawaii? It's stupid. It doesn't snow here. It doesn't get below freezing, except for like the top of the mountains every once in a while, right? There is absolutely no need that we have it for antifreeze in the cars. So, and there's lots of other places, like Southern California. It never freezes over, or Florida. Like, why don't we have, tropical cars or subtropical cars, that run off of, that have water as a coolant instead of ethylene glycol, right? I mean, that would be more environmental. Ethylene glycol is poisonous. So why don't we have water cars? And the answer is because ethylene glycol works better. Because it has a higher heat capacity, and because of that, you need a lower radiator, a smaller radiator. If you had a water-cooled car, your radiator would have to be bigger than with the corresponding size with antifreeze, because the antifreeze holds more heat, and you need less the smaller radiator to cool the engine. So, okay, so, oh, and I should also mention, when you talk about calories, so let's talk about heat units. We have a joule. The SI unit, the metric unit, is a joule, and a joule, I said a kilogram meter squared per second squared. That's a joule. And you might also see a calorie. A calorie is the heat for 1 gram of water to raise it 1 degree Celsius. So the heat capacity of water is about, depending on the temperature, it changes. But the heat capacity of water is about 1 calorie, which means it takes 1 calorie of heat will raise 1 gram of water 1 degree Celsius. So other units that we have for heat, there's a BTU, a British thermal unit. A BTU is the amount of heat it takes to raise 1 pound of water 1 degree Fahrenheit. So everyone knew what a BTU was. And there's also a ton, the TONNE, ton. That's the amount of energy it takes to raise, it's 2,000 BTUs. It's a ton of water 1 degree Fahrenheit. So a TONNE, like air conditioner units are usually listed in tons. Like, oh, this is a half-ton AC unit, and you can, it weighs about 50 pounds. We're like, how is this a half ton? It's like 50 pounds. It means the amount of energy flow per hour. It means you can draw 1 ton, 2,000 BTU, or a half ton would be 1,000 BTUs out of a room per hour. And nutritional calories, you'll see them in capital cals. So you say, how many calories are in this? And if you wonder, why are calories always capitalized? Because they're not calories, they're actually kilocalories. So nutritional calories, so when you have a chocolate bar that's 100 calories, it's actually 100 kilocalories. So that means that chocolate bar can raise 100 kilograms of water 1 degree Celsius. So that's a lot of energy. I mean, if you think about it, that's a lot of energy. If you've ever tried to, like, boiling water, I mean, it takes forever to boil water. So 100 kilocalories would also be the amount of heat it takes to raise from water from 0 degrees Celsius, a kilogram of water, 1 degree Celsius, up to boiling. So if you think about putting a liter of water on the stove and turning on the heat, how long is it going to take if you had ice water, well, water that didn't have ice in it, but at 0 degrees Celsius, up to boiling? That's a lot of energy, right? And that's the amount of energy that's in a candy bar, and the mini ones too, right? That's a lot of energy. So don't mistake how much energy is in food. Okay, so let's use this for heat capacity. Suppose you find a penny minted before 1982, because pennies now, they're zinc, they're copper-coated zinc. How much heat is absorbed when you take a penny from the snow, which is -8 degrees Celsius, to temperature of body, which is 37 degrees Celsius? Assume the penny is pure copper and has a mass of 3.10 grams. So let's talk about the system. Here's the system. Depends on what you pick for your system. If your system is the penny, the heat flow is positive. If your system is your hand, heat flow is negative. So it really depends. This part, it doesn't really matter. The system's going to become important later. But later on, when we talk about the direction of energy flow, that's going to become important later. But I have to look up the heat capacity of copper. This I don't know. What is the heat capacity of copper? I guess I could look. Let's Google that. Potato cannon. Nope. Okay. So, but anyways, so heat is equal to mass. So 3.1 grams times specific heat capacity. The specific heat capacity for copper is 0.385 joules per gram degrees Celsius. And then the change in temperature, delta T, this is always final minus initial. So when you talk about your change, it's always final minus the initial. So like if you're buying something, let's say you have $100 in your bank account, and at the end of the day you have $50. So what is the change of your money in your bank account? It's your final minus your initial. It's 50 minus 100, negative 50. If you had $100 at the beginning of the day, and then you had 150 at the end of the day, it's always final minus initial. It's 150 minus 100, positive 50. So delta change is always final minus initial. So we have final 37 minus a minus 8, like so. And then you put that in your calculator, and you will get 53.7 joules. So another thing, so 4.18 joules is equal to a calorie. So if you want to know the conversion there. So if you want to know, the easy way to tell is just divide by 4. So if you ever go to foreign countries, and I like to read labels on food. That's just myself. And like, I'm always kind of curious what's in stuff and how many calories it has. Some countries put energy in kilojoules. So if you ever look at that, I think New Zealand, for instance, has in kilojoules. I know in Hungary they do, but just depends. Okay, so recap for this one. So heat flow is equal to mass times specific heat capacity times change in temperature. So 3.1 grams of copper, heat capacity for copper, final minus initial, so body temperature 37, minus a minus 8, the initial temperature, so that's a change in temperature, and we get 53.7 joules. And that's not a lot of energy. 50 joules is nothing. So it may feel cold when you touch it, but 50 joules is nothing. So questions with this so far? Oh wait, I should erase this. I hate this one. This one's always a hard problem. I gotta cut this one. Okay. So here's an example of thermal energy transfer. A 32.5 gram cube of aluminum was initially at 45.8 degrees Celsius, submerged in 105.3 grams of water at 15.4 degrees Celsius. What is the final temperature of both substances at thermal equilibrium? So, assuming no heat transfer from anywhere else. So, this is what's going on. So, we have a block of aluminum and water. The water, we have 105.3 grams of water. The water is initially at 15.4 degrees Celsius. The block of aluminum is 32.5 grams of aluminum, and it's 45.8 degrees Celsius. We drop the hot aluminum into the cold water, and we let it sit. And we make sure it's thermally isolated. We put it in a cooler or something like that so there's no heat transfer anywhere else. And then after a while, we come and we check the temperature. And so we wait and see. And the idea here, so heat flow, so remember, we have the system. This way is positive, this way is negative. So the aluminum direction is negative, and the water direction is positive. So, we always have, this is, maybe you've heard the horror stories, like, I forgot a negative sign. Have you ever heard those horror stories when people talk about things? This is an example of one. If you don't have this negative sign, it's going to mess up your calculations. And the idea here is that the heat flow for the aluminum is negative direction, so it's minus, and the heat flow is mass, specific heat capacity, change in temperature. And so it's mass of the aluminum, heat capacity of the aluminum, and then change in temperature is final minus initial, final minus 45.8. So that's the initially of 45.8. This equals the positive heat flow for the water, the mass of the water, heat capacity of water, final temperature minus 15.4. So we have to solve now. Now we have to solve for TF. So how are we going to do this? We get all the TFs on one side and all the other terms on the other side. So we have minus M AL CS AL TF plus 45.8 mass AL CS AL equals mass of water, heat capacity water, TF minus 15.4, mass of water, CS of water. Then what you can do is we can add the TF to both sides and then add the 15.4 to the other. So we have 15.4 mass of water, CS of water, plus 45.8 mass of aluminum, CS of aluminum, equals mass of water, CS of water, TF, plus mass of aluminum, CS of aluminum, TF. And I can take TF out of here. TF, mass of water, CS of water, plus mass of aluminum, CS of aluminum. And then I can divide. So I'll just copy this. Nice thing about doing things on an iPad, you can copy them. So that you can divide it that way. So there's our final temperature. So this is like the algebra problem from hell here. So then you just plug in the terms. So that means our final temperature, mass of the water, 105.3 grams, times the heat capacity of water, it's 4.18 grams per, it's 4.8 degrees Celsius. It's joule. I'm sorry, are we doing joules? Joules per gram degrees Celsius times, it's plus. Plus 45.8. Mass of aluminum is 32.5. Heat capacity of aluminum. What is the heat capacity of aluminum? Heat capacity of aluminum is times 0.903 joules per gram degree Celsius. Oh, and I forgot 15.4. Shoot. Another nice thing about doing this, so 15.4 times that. I'm just following this number and I'm putting it down there. So mass of water, 105.3 grams times specific heat capacity of water, 4.18 joules per gram degree Celsius, plus mass of aluminum, heat capacity of aluminum, 32.5 times 903 joules per gram degree Celsius. Okay, so then we look at units. So with units, grams cancel here, so this is going to be grams. Grams cancel there. And grams cancel here. This is going to be grams cancel there. And there's joules in every single one. And looks like we have 1 over Celsius over 1 over Celsius. Is that right? So each one has inverse Celsius. So then the Celsius, that's weird because then the Celsius would cancel. Am I doing this right? Looks like I am. Oh, but the 15.4 and the 45.8, these are degrees Celsius. Okay. Okay, good. So these all cancel, and then the degree Celsius in the top stays. Okay, good. So the units work out. And then you put that in your calculator, and that's a tough one to put in your calculator. I guess I can do it, but then there wouldn't be enough space on my calculator to show you. Then that's 17.3 degrees Celsius is the final answer. So, as you can see, this one is easy per se because it's just setting two things equal to each other, but the algebra is tough. So, recap with this one. And the other thing, does this make sense? Does this make sense? We have hot aluminum, 30 grams of hot aluminum and 100 grams of cold water. And the water has a very high heat capacity, aluminum not so much. Do we expect the temperature to be closer to the water or closer to the aluminum? We expect the temperature to be close to the water. So it shows you a hot block of aluminum is not going to raise a water temperature up by very much. So going from 15 to 17, I don't know if I would notice that. If you gave me like 2 glasses of water, like, oh, that's a little warmer. Not that big a deal. Okay, so we have, we put a hot block of aluminum into cold water, and remember the system, energy flow in the system is positive, energy flow out of the system is negative. So heat flows from hot to cold. Then we have hot metal and cold water. That means the heat flow from the hot metal is negative. Heat flow into the cold water is positive by showing here. So minus QAL is positive Q water. And then we have the definition of heat transfer Q, mass times specific heat capacity, change in temperature, mass, water, specific heat capacity of water, change in temperature. We're looking for the final temperature, so final minus initial. And then we write all our terms, solve for final temperature, put in the numbers with the units, and we get 17.3 degrees Celsius. So another thing, when you look at things online, so you might be, you might say, okay, I need to find something like, what's the heat capacity of this substance? It might give you the heat capacity in something like, I don't know, calories per mole Kelvin, for instance. So for you have to be able to change the units. And you already know how to do that with dimensional analysis, right? So change the units from calories, and if it's water, if it's moles, there's 18 grams of water in a mole of water. So you can change it that way. Another thing, unit-wise, so for a unit, degrees Celsius equals a Kelvin. So that means, so when you multiply and divide Celsius and Kelvin, they can cross-cancel. But if you, that as a unit, not in terms of the magnitude though. So if you can't use them if you need the magnitude. So 0 degrees Celsius is 273 Kelvin. That is not interchangeable. But a change of 5 Kelvin is the same thing as a change of 5 degrees Celsius. So, and if you do that in multiplication and division, you can take the units out that way. Does that make sense? All right. And so, how you guys doing so far? I'm trying to read your faces. You don't look you look kind of bored, actually. Sorry, I guess I'm not showing my typical enthusiasm. So pressure, volume, work. So now we're going to talk about work. And one of the ways you can do work, it's with change in volume. So as you, and also it depends on the system as well. So work, and this is a definition in the book, work is equal to pressure times change in volume. So you breathe in, trying to breathe in, and your lungs get bigger. So breathing in, your lungs get bigger, and your volume, final minus initial, is bigger than at the end. So final volume minus initial volume. And then exhaling, and the question is, how much work am I doing when I exhale? So my lungs shrink, and I can feel myself pushing the air out, and my lungs get smaller, and as it's getting smaller, it depends on my breath is doing work out in the system, or how do I put it? Or if you're the system, where's the work going? So is it leaving the system, or is it going into the system? So it takes energy to inhale, exhale, releases energy. Okay, so to inflate a balloon, you must do pressure or volume work on the surroundings. If you inflate a volume from 0.1 liter to 1.85 liters against an external pressure of 1 atmosphere, how much work is done in joules? So the idea here, minus P delta V, so is equal to minus, so an atmosphere times change in volume, it's final, 1.85 liters minus 0.1 liters. So this equals minus 1.75 liter atmospheres. And what the heck is a liter atmosphere? So one of the ways you can convert this is the conversion is 1 to 1.3, but you can use the values of R. So if we need liter atmospheres, so we can convert this by minus 1.75 liter atmosphere times, so we need liter atmosphere in the bottom. So we have 0.08206 liter atmosphere over mole Kelvin, and R is also 8.314 joules per mole Kelvin. The mole Kelvins cancel, and it's that cancels. And so I do the liter atmospheres, and or you can just know the conversion is 101.3 joules per mole Kelvin. But if you forget, that's how at least that's how I remember it, at least, is by the fraction of R's. And then this is minus 177 joules. So, and this also seems kind of weird because as I'm blowing a balloon up, right? I'm blowing a balloon, and what happens? The balloon gets bigger. But like, why is that negative? Why is the heat? Why is the energy flow negative for that? Because the balloon is pushing the air out of the way. So if your balloon is a system and it gets bigger, it pushes. It does work on the atmosphere to push the atmosphere out of the way. That is the direction of the heat flow. So then again, it also depends on your definition of the system. So you can tweak it that way. So questions with this? How to use this? No. Okay. And so remember when I said that energy? Remember when I said energy is a state function? Remember when I said that? So it means that it doesn't matter what pathway you take. Internal energy is the same. And have you ever wondered, like with food, you'll say like, oh, this is low calorie. So like it used to be, if they've also changed some of the labeling. They used to say like, I think it was Diet Coke used to say 0 calorie. Now they don't say that anymore. If you've never noticed that, they say it's low calorie or something like that. If you look at diet soda drinks, and then I hate diet soda drinks, to be honest with you, but you'll see look at the calories in them, and it'll say it has like 5 calories. So if I drink this Diet Coke, I get 5 calories. And where do they get that number? They get that number from a bomb calorimeter. Let's just take a picture of one. I have it right here. Rather than try and draw one, someone's already done it for me. So here's a bomb calorimeter. That doesn't, all right, I'll just zoom in on it. Okay, so here's a bomb calorimeter, and you have your sample. You have oxygen in, oxygen out, or air in, air out, and then you have a thermometer, and you have water inside of it, and it's stirring. You have a stir rod, and then you take whatever it is you have in here, and you burn it. So you burn whatever your sample is here, and then you burn it in the presence of oxygen, and then the energy from this goes around this water bath and this insulated thing. They're fat. Like the ones that I've seen, they're about this big, and the walls they're heavy, they're fat, and they're really thick walled. So they're really good at keeping their heat in. And you burn whatever it is in here, and you figure out what the energy flow is from that. And since energy is a state function, that means that if you burn something like, I think we're going to do sucrose the next problem. If you burn sucrose in this, burning sucrose in air with oxygen, the energy change in that is the same that you get in your body. So meaning if I burn sucrose in my cell's mitochondria using the citric cycle, the change of internal energy, and if I eat sugar, I exhale carbon dioxide and water, right? So it's coming in sugar, leaving carbon dioxide, water. It has the same reactants, same products. The pathway is different. So, of course, the work and heat is different, but the change of internal energy, the calories of that, do not change. Doesn't matter if I burn it or I put it in my body and then go jog a mile or take a nap or something like it. The energy change the same. Doesn't matter. Because of that, they take these sweeteners like sucralose, various ones, and they put it into a bomb calorimeter and they burn it. And it has calories in it. But the question I always had was, do we actually burn it? Like, can my cells take sucralose, Splenda, and burn it and actually get energy from it? Can I get energy from Splenda? And I don't know if there's, I don't think we can, to be honest. But that's why they have calories in them now. So we have that now. We have 1.01 grams of sucrose undergoes combustion in the bomb calorimeter. The temperature rises from 24.92 to 28.33 degrees Celsius. Find the heat of a reaction, the delta E, the change in internal energy reaction for the combustion of sucrose in kilojoules per mole sucrose. The heat capacity of the bomb calorimeter determined in a separate experiment is 4.9 kilojoules per degree Celsius. So, all right, and let's talk about something here. So we have, maybe I'll make my pen tip fatter. We have our system, and then we have the energy flow. So our system, we're going to call our system is the sucrose. The system is the sucrose, and that means that also with the sucrose, the delta E of the sucrose is negative. So I should say, for me, myself, the way I approach this problem, I approach it in the right-brained way of doing it. The textbook kind of goes the left-brained, the very exact numbers. For me, I always look at the system and look where the heat is flowing, and then I assign the appropriate values that way. So if you're wondering why I keep on, what's the system, where's the heat flow, that's kind of the right-brain approach to solving the problem. So our system is the sucrose, and I know that the energy flow from the sucrose is negative, part of it because I know sucrose is a fuel. The other thing that I know is the temperature of the bomb calorimeter is going up. If the temperature of the calorimeter is going up, that means heat is being absorbed. Heat flow is positive for the calorimeter, and that means that the reaction's heat flow has to be negative. So the delta E, this is negative, so negative delta E equals the heat flow. And also the heat flow for the calorimeter. Remember when we had mass, specific heat capacity, change in temperature? So it says here the heat capacity is 4.9. So there's another equation that I had in the beginning that I just had heat capacity change in temperature. And I said that the heat capacity can be mass times the specific heat capacity. Since the bomb calorimeter, it's not just one thing. It's not just water, it's not metal. It's a bunch of things. So because of that, you have to take the whole heat capacity of that. So you can't just, it's not just one thing. If it was just water, we could use the specific heat capacity, but it's metal, it's water, it's insulation, it's a thermometer, it's an ignition wire, all these kind of things. So we have to use that heat capacity. So, okay. So the change in internal energy is equal to minus the heat capacity. So let's figure out what the heat flow is. The heat flow, it's the heat capacity, 4.9 kilojoules per degree Celsius. And the change in temperature is final minus initial, 28.33 minus 24.92 degrees Celsius. And that means the heat flow of this is going to be 16.7 kilojoules. And the heat flow of the calorimeter, if you want to do, this is the left brain approach, is minus the heat flow of the reaction. So that means our reaction is minus 16.7 kilojoules. So for me, though, I knew that the reaction is going to be negative because of the fact that it's exothermic. Exothermic means heat's leaving the system. So you have minus 16.7 kilojoules times, this is for, this is per 1.01 grams of sucrose. And so this is just the ratio. So which means when I took 1.01 grams of sucrose, I released 16.7 kilojoules. But then if I multiply by 342, that's the molecular weight of sucrose, gram sucrose per mole sucrose. And this dimensional analysis, I get minus 5.66. Well, let me just write this here. 566 kilojoules. No, I'm sorry, it's another zero. I'm reading the textbook. Kilojoules per mole sucrose. And the sig figs then. Okay. So this includes ratios as well. All right, so we took 1.01 grams of sucrose and we burned it in a bomb calorimeter. And we want to know what the change in internal energy is for sucrose. And so this works for all sucrose. Change of internal energy is path independent, doesn't change. So we burn in our bomb calorimeter. And one thing we noticed about bomb calorimeter, it went up in energy. So if the bomb calorimeter goes up in energy, that means that it's absorbing energy. Energy flow is positive into the bomb calorimeter, which means energy flow leaving the sugar as it's burned is negative. But then we got to figure out the heat flow into the bomb calorimeter. We use heat flow as heat capacity times change in temperature. We are given the heat capacity. Change in temperature is about 3 degrees Celsius. So we get the heat flow into the bomb calorimeter is 16.7 kilojoules. And that's 16.7 kilojoules per 1.01 grams of sucrose. So negative flow because it's leaving the system. Talk about the sugar is leaving the system. And so this is 16.7 kilojoules per 1.01 grams. And we multiply it by the molecular weight of sucrose to get the amount of energy per mole of sucrose. So it's minus 5,660 kilojoules per mole sucrose. So questions with how this works? It just makes so much sense. Well, let me try and explain some of this too. Here's some of my drawing. So if you have a hard time remembering this, so like insects have exoskeletons. It's like armor. So an exoskeleton is an outside skeleton, right? And exothermic, so exothermic, outside, exo is outside, thermic, therm, temperature. Exothermic is like a fire. You feel fire, heat's flowing from the fire. That's exothermic. We have endoskeletons, right? I can feel my bones in my hand. So, and endo means inside, and so endothermic means that you're taking energy in, and energy flow is positive that way. So think of the directions. If you have a hard time remembering what the directions mean, think of them that way. But here is a problem for you. 18 grams of glucose burns in a bomb calorimeter. 1 kilogram of water raises from 10 degrees Celsius to 7 degrees Celsius. Heat capacity, specific heat capacity for water is 4.18 joules per gram degree Celsius. What is the change in internal energy for the reaction of glucose? And the thing with glucose, it's 180 grams per mole. And you have heat is mass, specific heat capacity, change in temperature. Delta T is final minus initial. I don't watch TV anymore. I just watch Netflix and stuff. Do they still have Who Wants to Be a Millionaire on TV? Or did you ever watch that? Or, oh geez, am I that old? That's not cool anymore? All right, because they used to have multiple choice questions, and then one of the things you could say, like, eliminate 2 answers is one of the things you could do. If I were to eliminate 2 answers, what are the easiest ones to eliminate? Is the heat flow for the sugar, for the glucose, is it positive or negative? It's negative. So we know right away it's not B or D. Sounding building that's A, negative 2,500. Everything at C, minus 5,000. All right, I guess I'll come around. Anybody stuck? Just need more time? All right. Okay, so let's say you did 18 grams and raising 20 dollars much. What if we did 10 grams? It would be a different. Yeah. Because this one here, so if you look at this problem, we said go over 1 gram to figure out what the energy of the reaction is. The units of the reaction is right, we start with grams and we go to moles reaction. So what you did was figure out the heat flow for 1 gram and then multiply it by 342 to get to be so it's the same thing going on here. The energy flow, this ratio, and multiply by 1 to get energy flow. Take a look at the diet and other things. I do. And how many calories are in flour? So 1 cup of flour has 455 calories. Okay, so I'm very careful when I watch that movie, right? So it tells me that this is right, this is a unit like in units. And let's say I want to know per mass. So it's 0.35 calories and a cup of flour. Oh, this is 125. So if I want to know the mass where is it? So this is 400 So the system. So it's a system energy flow in the system is positive. Energy out of the system and the water is increasing. So when water is hot, it's actually exothermic is energy leaving the system. So endothermic is energy into the system. So and exo is negative, endo is positive. So meaning the calorimeter. So this one here, the sugar, the green stuff, that's negative. The energy in the apparatus is positive. That is confusing. Yeah, that's very confusing. Yeah. So two subjects. You start with 18 grams. You follow? Yes. Okay, you guys. Okay. Yep. All right, good. Everyone's getting it. It's A. And a point of confusion. So here's the lime green is the sugar, and the energy of the sugar, it's leaving the system. So as the sugar is burning, it's exothermic. The energy is leaving the system. For the apparatus, it's positive. So that's the energy is going into the apparatus and raising the temperature. So that has to do with the direction of the flow. So I know that is confusing. And to be perfectly honest, I screw it up all the time. That's why if you see me talking like, where's the heat flow? Where's the heat flow? I'm always asking myself where the heat flow is, because that's what I have to do to solve these problems. Because once you get one of those negative signs wrong, you're like, oh man. It's like the the learning of it. All right. Sorry I went over that. How are we doing? Questions so far? Okay. Now it's time to invent a new term. So we're going to invent a new term called the enthalpy. The enthalpy, and we give it the term H, and we define enthalpy as H is equal to the E, the internal energy, plus the pressure times the volume. Okay? And also, is anyone here in Calc 1? So have you done the differential rule, the addition rule for differentiation? Yeah, here's an application of the differential rule. So if you take the derivative, and if you don't understand this, it's okay. This is a calculus concept. And I know calculus is not a prerequisite for this class, That doesn't mean there's not calculus in this class. So if you take the derivative of both sides, what do you get? You get dH equals dE plus dPV plus dVP, right? That's when you take the PV prime, I'll make my pen smaller. So take the derivative of PV, you take the derivative of this. What is it? It's P prime V plus V prime P. That's the addition rule. And it says under constant pressure. So under constant pressure, there is no change in pressure, so that term goes away. And you're left with derivative of volume times the pressure, which is right there, right? The change, but not necessarily the macroscopic change. So differential of the enthalpy is differential of the energy plus the pressure differential volume. So that's the addition rule. If you're wondering where that came from, it's a calculus proof. But don't worry, I won't throw too much calculus in this class. But anyways, so we define a term. And I mean, we can define anything we want. So enthalpy, we call this energy plus pressure times volume. And then at constant pressure, delta H is delta E plus P delta V. And also, let's do this more. Delta E is by the first law. By the first law, it's the heat plus the work. And P delta V is minus work. So that means that delta H, this enthalpy term, is exactly equal to the heat flow at a constant pressure. So that's, and quite frankly, we use enthalpy more frequently than internal energy because, among other things, it's easier to measure. It's real easy to measure heat flow. It's not so easy to measure work, right? So I mean both in simple chemistry laboratory and work in general, because work is, it's a differential path length. So you ask yourself, like, if I wanted to say, how much work did your car do on the way to school? And, you know, that would be a really hard thing to figure out. Because you're driving your car, you're turning your car, you're braking, you're like, okay, I've done work there, but I've taken work away when I braked the car, and then that work went to something else and did all that, and that would be a really hard thing to figure out. You know how if someone actually made me figure out what the work was? I would take the energy of gasoline, then I would measure how much heat my engine put out, and then I would subtract that from the energy and get the work that way. That would be much easier than directly figuring out the work. So that's one of the reasons why we use enthalpy so much, because it's easier to measure. It's just the heat flow. So okay, so enthalpy, we do this, and it's one thing I love about thermodynamics. They make up new terms, and use the delta H. And here are some things for delta H. So the value of delta H, enthalpy. So enthalpy is the way you say this. Enthalpy for chemical reaction is the heat absorbed of the reaction under the conditions of constant pressure. And constant pressure is usually, oh, is it time to go? Stop? It is. We got 1 minute. Well, it's 1 minute by Sprint, or not Sprint, by Google Prime or whatever and I'm like, okay, I guess I need to shut up now. All right, I will finish up here on Wednesday.